Hello, welcome to Guidancee Education Channel. We are continuing Chapter 1, Solids, under Class 12, Chemistry. In this video, we are going to discuss packing efficiency and packing fraction of different types of cubic unit cells. Let us see the subtopics. Definition of packing fraction and packing efficiency. Calculating packing fraction and efficiency of cubic cells. Under this heading, we will discuss three types: packing fraction and packing efficiency of simple cubic cells, packing fraction and efficiency of face-centered cubic cells, packing fraction and efficiency of body-centered cubic cells. This topic is very important, so watch the video completely without skipping so that you get all points cleared. And if you think the video is useful, like the video and share the video with your friends who may also be benefited. Do not forget to leave your comments in the comment box below. If you have not subscribed, subscribe my channel now and press the bell button so that you get intimated as soon as videos are posted. Thank you very much. Calculate the packing fraction and packing efficiency of simple cubic unit cell. This is the open structure of a simple cubic cell. This is the space filling structure of one face. Definition of packing fraction and packing efficiency. Packing fraction is a ratio of the volume of the particles in the unit cell to the total volume of the unit cell. We know how to calculate the number of particles in a particular type of unit cell. From that, you can calculate the volume occupied by those particles in the unit cell. The volume of the unit cell can be calculated from edge length. The percentage of packing fraction is called packing efficiency. This is the edge length, which is marked as A. It is the distance from the center of particle in one corner to the center of the particle in the next corner. This length is A in space filling structure. The distance from the center of the particle to its periphery is what you call radius, marked as R. It's one radius of this particle and this is one radius of the next neighboring particle. So we can write A is equal to 2R. The number of particles in the simple cubic unit cell is equal to 1. Volume of sphere. Particles are considered as spheres is equal to 4 by 3 pi r cube. Volume of unit cell. A raised to 3 equal to 2r the whole raised to 3 equal to 8r cube. So packing fraction is equal to 4 by 3 pi r cube divided by 8 r cube. R cube and r cube get cancelled, equal to 4 pi by 3 into 8. 4 and 8 get cancelled, 2. So pi by 6. The value of pi is 22 by 7. So this is equal to 0.524. So packing fraction is equal to 0.524. So this is one answer. Packing efficiency is packing fraction into 100. So that gives 52.4%. This suggests that in the whole volume of the unit cell, only 52.4% is occupied by the particles. The remaining is vacant. That is about 47.6% is vacant. We know in close packing a certain number of voids are produced, and in this case the volume of the voids altogether is equal to 47.6. Packing efficiency is the volume used up by the particles. I hope this is clear. Calculate packing fraction and packing efficiency of FCC unit cell. This is the FCC unit cell. I have shown the face-centered particles with white dot so that you can identify them easily. In space filling structure, this face-centered particle is in contact with the corner particles. I have shown here open structure. We have to approach this problem slightly different from how we approached the previous problem. This is the radius of the sphere marked R. This is the edge length A. It is the same for all edges because it is a cube. Edge length A is equal to 2R. This is the top face diagonal. This corner is A, this corner is B, and this one is C. ABC is a right angle triangle. AC is equal to root of AB square plus BC square. We are using Pythagoras theorem. AB and BC are all edge lengths. So root of A square plus A square equal to root 2A square equal to root 2A. But AC is equal to 4R, the radius of the two corner particles and the diameter of the face-centered particle. So 4R is equal to root 2A. From this, A is equal to 4R by root 2. Volume of the unit cell is equal to edge length raised to 3, that is A cube, equal to 4R by root 2 the whole raised to 3, equal to 4 into 4 into 4 into R raised to 3 divided by root 2 raised to 3, which becomes 64 R cube by 2 root 2. On further simplification, it becomes 32 by root 2 into R cube. This is the volume of the unit cell. You can see it depends upon radius of the particle. Number of particles in FCC is equal to 4. So total volume of the particles in FCC will be equal to 4 into 4 by 3 pi R cube. Packing fraction becomes equal to 4 into 4 by 3 pi R cube divided by 32 by root 2 R cube. R cube and R cube get cancelled. On simplification, 4 into 4 pi into root 2 by 3 into 32 equal to pi by 6 into root 2. On simplification, 0.74. Packing fraction is 0.74. Packing efficiency is the percentage of packing fraction, that is packing fraction into 100 equal to 74%. That means only 26% is vacant. This is more efficient than packing in simple cubic unit cell. For HCP also the packing efficiency is 74%. I hope this is clear. Calculate packing fraction and packing efficiency of body-centered unit cell. This is the body-centered unit cell. This is the particle at the body center. Note the corner points A, B, C and G. This is the face diagonal AC and this is body diagonal AD. ABC is a right angle triangle. ACD is another right angle triangle. AC is equal to root of AB square plus BC square. But we know AB and AC are edge lengths. So equal to root of A square plus A square equal to root 2A. We have seen this in the previous case. This is for the face diagonal. For the body diagonal, we have the right angle triangle ACD, where AD is equal to root of AC square plus CD square. AC is equal to root 2A. So AC square is equal to 2A square. CD square is equal to A square. So root of 2A square plus A square equal to root of 3A square. This is equal to root 3A. From the diagram it is clear that AD is equal to 4R. We know edge length A is equal to 2R. So 4R is equal to root 3A. So A is equal to 4R by root 3. Number of particles in body-centered cubic cell is equal to 2. Volume of the unit cell is equal to a raised to 3 equal to 4r by root 3 the whole raised to 3 equal to 4 into 4 into 4 r cube by root 3 raised to 3 equal to 64 r cube by 3 root 3. Total volume of two particles is equal to 2 into 4 by 3 pi r cube. Packing fraction is equal to 2 into 4 by 3 pi r cube. The whole divided by 64 r cube by 3 root 3. R cube gets cancelled. This is equal to 2 into 4 pi into 3 root 3 by 3 into 64. This on simplification becomes pi by 8 root 3. The value will be 0.68. This is the packing fraction. You know pi is equal to 22 by 7. I will carry over this on the top. This is the first answer. Packing efficiency is packing fraction into 100. So it becomes 68%. This is the answer for the second part. This means 32% of space is occupied by voids. This type of packing is less efficient than FCC and HCP, but more efficient than simple cubic packing. I hope these points are quite clear. We will meet in the next video with the next topic. Thank you.